We learned in general chemistry that acids and bases can be strong or weak. And remember that strong acids are completely ionized in water, but weak acids are partially ionized in water. And why do we care about strength of acids and bases? Because that helps us to predict how the reactions will proceed. There are different ways to analyze the strength of acids. One of them is quantitative strength analysis. In this method, we compare the pKa values for different acids to compare the strength of them. And we can do qualitative strength analysis. In this method, we have to check the structure of the acids and compare the stability. And we will go over both of them. In quantitative analysis, we just need to have the pKa values, and the lower pKa value corresponds to the stronger acid. For example, here H2SO4, sulfuric acid, has the smallest, lowest pKa value, which means H2SO4 is the strongest acid. And then among these compounds, these acids that we have in this slide, ethane, this compound, has the highest pKa value. pKa of ethane is 50. So ethane is the weakest acid among these acids. pKa values help us to predict which direction of the equilibrium will be favored. Here we have reaction of hydroxide. This is hydroxide with acetic acid, and products are H2O and acetate. So hydroxide is base and acetic acid is the acid. On the other side of the reaction, H2O is conjugate acid of hydroxide, and acetate is conjugate base of acetic acid. So we're comparing these two acids, acetic acid and H2O, and we have the pKa values. pKa value for acetic acid is lower, it's 4.75, and pKa value for H2O is 15.7. We know that the stronger the acid, the lower the pKa values. And in this reaction, acetic acid has lower pKa values, so acetic acid is the stronger acid and H2O is the weaker acid. Stronger acids ionize more than weaker acids, which means stronger acids are less stable than weaker acids. And here in this reaction, acetic acid is the stronger acid, which means it is less stable than H2O. It ionizes, dissociates more than H2O, and reaction favors the products. In acid-base reactions, equilibrium moves toward the side with weaker acid and weaker base, because weaker acids and weaker bases are more stable, so reaction goes toward that side. In this reaction, equilibrium moves toward the products because products are more stable, and the arrow that goes toward the products is longer, and the arrow that goes toward the reactants is shorter. That means that equilibrium favors the products. If the pKa values of the acids are not available, we have to do qualitative analysis. In this type of analysis, we compare the stability of the structures to find out which acid is stronger. In order to do qualitative analysis, first we find the conjugate base of each acid. So, for example, we have HA1 and HA2, these two acids. We don't have the pKa values. First, we find the conjugate base of HA1 and conjugate base of HA2. Remember, conjugate base forms when acid loses a proton. Here, HA1 loses a proton and conjugate base is A1 with a negative charge. HA2 loses a proton and conjugate base forms, which is A2 with a negative charge. Now we compare stability of conjugate bases A1 and A2. Which one is more stable? More stable conjugate base corresponds to the stronger acid. Now the question is, what makes a conjugate base more stable than the other one? The conjugate base that can stabilize its negative charge more effectively is more stable, and it corresponds to the stronger acid. The factors that affect the stability of a negative charge in order of priority are type of atom that carries the charge, then resonance, then induction, and finally type of orbital. And usually this is the order of priority. Type of atom is the most important one and type of orbital is the least important one. But of course there are some exceptions. We can use acronym ARIO to remember the order. A for type of atom, R for resonance, I for induction, and O for type of orbital. Let's check the first factor, which is type of atom. We have butane and propanol, and we want to find out which one is a stronger acid. First, we find the conjugate base for butane and conjugate base for propanol by removing a proton from each compound. In conjugate base of butane, negative charge is on carbon, and in conjugate base of propanol, negative charge is on oxygen. The type of atom that carries the negative charge is different. When we check the periodic table, we see that carbon and oxygen are in the same row, which means they have similar sizes. And oxygen is more electronegative than carbon. So oxygen can stabilize the negative charge better than carbon. So negative charge is more stable on oxygen than on carbon. If the atoms that carry the negative charge are in one row of periodic table, electronegativity is the dominant factor. For example, carbon and oxygen. They are in one row of the periodic table, and oxygen is more electronegative than carbon, and negative charge is more stable on oxygen. Remember, the more stable conjugate base corresponds to the stronger acid. Here, this is the more stable conjugate base because oxygen is more electronegative than carbon and negative charge is more stable on oxygen. So this is the more stable conjugate base, which means propanol is the stronger acid. Now let's compare the acidity of HCl, hydrochloric acid, and HBr, hydrobromic acid. Which one is a stronger acid? Again, first we have to find the conjugate base by removing a proton. Conjugate base of HCl is chloride, a chlorine with a negative charge, and conjugate base of HBr is bromide, a bromine with a negative charge. And when we check the periodic table, we see that chlorine and bromine are not in the same row. They are in one column, which means they don't have similar sizes. And bromine is larger than chlorine. Larger atoms spread the charge over a larger volume of space, which makes the charge more stable. In this example, we have chloride and bromide has a larger size. Bromine is larger than chlorine. So bromide is more stable than chloride. Bromine makes the negative charge more stable than chlorine. And again, remember, more stable conjugate base corresponds to the stronger acid, and HBr is a stronger acid than HCl. When we are checking the type of atom, if the atoms that carry the negative charge are in one row of periodic table, electronegativity is the dominant factor. And the more electronegative atom makes the negative charge more stable. If the atoms that carry the negative charge are in one column, size is dominant, and larger atom makes the negative charge more stable. The second factor that stabilizes the negative charge is resonance. Resonance will spread out the formal charge into partial charges, and this will stabilize the formal charge. Let's compare acidity of ethanol and acetic acid. First, we find the conjugate base for each compound, for each acid, by removing a proton. Then we have to identify which conjugate base is more stable. When we check these conjugate bases, in both of them negative charge is on oxygen. So type of atom that carries the negative charge is the same, which means we have to check the second factor, which is resonance. Negative charge in ethoxide in the first conjugate base doesn't have resonance, but negative charge in acetate, the second conjugate base, has resonance with the carbonyl group. So one of the lone pairs of the oxygen can form a pi bond with carbon, and now this pi bond of the carbonyl breaks, and both electrons will collapse on oxygen, and this is the resonance contributor. As you can see, resonance makes the acetate more stable than ethoxide, and more stable conjugate base corresponds to stronger acid, which means acetic acid is a stronger acid than ethanol. Identify the stronger acid. Here we have acetic acid and trichloroacetic acid. So first we find the conjugate base for each of them by removing a proton. Negative charge is on oxygen in both conjugate bases, and both of them have resonance. In both of them, a lone pair of oxygen can form a pi bond with carbon, and pi bond between carbon and oxygen will break, and both electrons collapse on the other oxygen. The first two factors that affect the stability of the negative charge are the same. Type of atom is the same. They're in both of these conjugate bases. Negative charge is on oxygen, and resonance is the same. They both have resonance. So we have to check the next factor, which is induction. Electronegative elements like chlorine pull electron density away from the negative charge through sigma bonds and stabilize the negative charge, and this is called induction. So induction works through sigma bonds. Between these two conjugate bases, the second one with chlorines is more stable because it has 3 chlorines that withdraw the electron density away from the negative charge and make the negative charge more stable. So this one is more stable. And again, more stable conjugate base corresponds to the stronger acid. Here we have 3 compounds, ethane, ethylene, and acetylene. And we want to compare the pKa values and explain the difference between pKa values of these 3 compounds. When we check the pKa values, ethane has the highest pKa value and acetylene has the lowest pKa value, which means that acetylene is the strongest acid and ethane is the weakest acid. To explain the difference between the pKa values, first we find the conjugate base for each of these compounds. Now we compare the conjugate bases. In all of these 3 conjugate bases, negative charge is on carbon. So type of atom is the same and it doesn't help us. The second factor that we check is resonance. None of these conjugate bases have resonance, so resonance is out too. The third factor that we check is induction. Induction is pretty much the same for all of these 3 conjugate bases, so we have to check the fourth factor, which is type of orbital. Here negative charge is in sp3 hybrid orbital. In the second conjugate base, negative charge is on a carbon, which is sp2. And in the third one, negative charge is on a sp carbon. sp carbon has more S character. It's 50% S, 50% P. sp2 is almost 33% S character and around 66% P character. And sp3 is 25% S and 75% P character. So sp orbital has more S character and it is more electronegative. More S character corresponds to a higher electronegativity. So sp orbital is more electronegative than sp2 and sp2 is more electronegative than sp3. And this explains why conjugate base of acetylene is more stable than conjugate base of ethylene and ethane.